Hi everyone. Today we continue our exploration of Wordle, but now finally we have everything working, right? If I go down here and say Cabal test, then it's going to spin a little bit, and I certainly hope it says test passed at the end of this run. And what that means is that we have a system now that can do our Wordle analysis, find the best word. If you didn't watch the last video, the best word according to this particular analysis, there's other analyses, but the best first word is raise. So we've gotten this far, but actually it still takes about a minute or so to figure out what that best word is. I think we can do better. So what this, and actually I think the next few videos are going to be about, is about optimization. So today we're going to sort of set things up so that we can start to measure the performance of our program and do a little bit of general setup. And I have one optimization in mind that I expect will yield good results. I have another optimization in mind. I don't know if that's going to be next week or in 2 weeks, because the other thing I want to do is demonstrate the criterion library for getting really nice performance analysis of Haskell programs. We're not going to do criterion today, but perhaps next week. So let's just get a general setup. So one challenge with doing performance testing is we need to have a reliable thing to test. So to do that, instead of running in GHCI, which is not optimized, what we need to do is create an actual main which will run, and then we can test that running program, and that's gonna help us a lot. So we're gonna go back into our Cabal file here, and we have a library, and it's been a long time since we've looked, but there's actually this little executable section. So let's take a look at main.hs. Oh dear, there's two of them. I don't know which one I want. Which one do I want? I want main it's not in any sort of subdirectory. Oh, okay, hold on. Let's just make sure I have this right here. I want Wordle, because I think I made this mistake another time. And then there's here exe. Aha, because it's an HS source here. So this is our main. And this was where we started. There was some experimentation we did, just printing things out, making sure basic things were working. We're going to delete all of this now. And instead, now that we have a working system, all I really want to do is just figure out what is this first guess. This is going to be a nice sort of stress test of our system. The very first guess, figuring out what that best thing is. On the one hand, we could just do it once and be done with it. But on the other hand, that's going to be the hardest test of our system because we haven't eliminated any words from contention. So to do that, we need to call max expected value, and then all we have to do is pass in the vector of possible words. And so that seems pretty easy. So if I go over here to main, I can call max expected value of final words. So if you've been paying close attention, you might know that there's final words and guess words, right? Wordle allows you to guess words along the way that it's never going to use as the final word. These are less common words, less common 5-letter words that it will allow you to guess, but it's never going to sort of expect you to guess, I suppose. I'm not going to worry about that distinction right now. Maybe we'll come back to it, but just using final words is enough to be able to do this performance analysis. So let's import words. We have to import Wordle. And now there's still, I can't just run this. I have to print something. So what does this return, this max expected value? Okay, so this has actual type Wordle word. And I don't want it. Well, no, I do want that. I can just say print, can't I? There we go. That looks like actually a decent main program. So now if I go down here and I do Cabal build, it will chug a little bit and it will compile this. And then I can say Cabal run. Oh dear. The run command is for running a single executable at once. That's what I want. The target refers to the package which includes the executable. Okay, Cabal run Wordle. That's what I want to do. And now we have to wait. And now we have our answer. So it took maybe a minute or so. And now that we have this set up, we actually have something that we can start testing. But before we go any further, there's a critical thing that we have to do, and that is start taking notes. When I have observed other people doing performance analysis and optimization, this is the single biggest failure that I see out there. It's failure to take good notes. We're going to start a new file here. Let's save this. I'll just call it perf.txt. I don't want it in the exe directory. I just want it in Wordle. And this is where we're going to write down our observations. So this allows us to remember what we've done so we can go back and look at it later and then compare later results to early results. And we know what we're talking about. It's so easy to say, oh, I'll just remember this. I'll remember it. It'll be okay. You never do. You never do. So let's take some notes. So initial run here takes about a minute. Well, that's pretty poor, isn't it? Let's see if we can do a little better than takes about a minute. And we can use the utility time, which will tell us how long it takes to run. So let's do that by doing time cabal run Wordle. So clearly my time estimation is terrible because it only takes 20 seconds, not about a minute. But now we can say, okay, so the initial run takes about a minute. Actually, no, measured at, we're going to take that top number, the real number, 19.341 seconds. Or maybe, no, maybe I'll do user. Measured at user, so I'm going to write down my choice here, 968 seconds. Okay, so a better test would actually run this multiple times because there could be other things going on in my system, like recording this video, that might be slowing things down. I'm not going to do that now. That would be slightly better. Again, later we're going to look at Criterion, later video. We're going to look at Criterion, which actually does repeat runs. Okay, so this is our baseline. But actually, to even measure a baseline, we need to know what it is that we're measuring. So another great thing to do is to make lots of commits as you're doing performance testing. So let's see, do we have anything to commit here? Well, there's this perf.txt. And then, let's see, there's some other things that are modified. Let's just do that, and we're going to make a commit right now. And initial perf test. And then the key thing is to remember the commit number, measured commit this. So now we can go back and see exactly what we measured. Okay, so this is our baseline. That's okay. I mentioned a minute ago that time is kind of a funny thing because depending on what other operations are running on my system, it might vary, maybe even by a lot. So on that particular one, I kind of sat still staring at the screen. Maybe if I ran it again but did a lot of movement, the video capture would take more effort from my computer. So I want to change from measuring time to measuring allocations. Basically, whatever you do in Haskell allocates more memory, which will then get garbage collected. And so because Haskell is an immutable language, we don't often change things in place, although it is possible. So most of the time, the number of bytes allocated during a run of a Haskell program is closely correlated to the amount of time it takes. And so looking at allocations makes an excellent proxy for measuring time. Time is really the thing that we want in the end, but measuring allocations means that we have a reliable, repeatable mechanism by which to measure our performance. So instead of running, let's see, cabal run Wordle, what I really want to do is I want to run this, and then, I need to pass RTS options. Ugh. If I do this, I think I can say cabal run and then dash Wordle, maybe plus RTS dash T will give me information. Let's see if this works. Aha, it did. So here we see exactly how many bytes our program had to allocate, and it's quite a lot. So here, this is actually, let's do this. Let's not take my estimation. So measured with time, allocations. Whoops, I don't want that information. I want down here this number of bytes. I'm always just going to measure it as bytes. And so this is a number that we can watch. If I ran this again, we would reliably get the same or very similar, should be the same, I would imagine, for something like this, the same number of bytes allocated. Okay, so now that we have this basic setup, I want to look at an optimization. So one optimization that I realized actually while I was recording the last video is that in this partition function, this is the function that goes through and figures out what response we would get from each potential answer and then puts them into groups, and then we can look at the individual groups to figure out which guess is going to give us the best chance of, or the highest expected value of removed words. But this partition words, it creates a list of Wordle words, and then in the key function, the expected value or max expected value, that calls expected value of guess. Expected value of guess calls expected number of eliminated words, which doesn't work over words at all. It's just working over these a list of ints, where each int is the length of a partition. So here we have to call get length. So after all of this work building up these lists, we just go and then measure the length of the lists. So I want to go and change partition words not to build up a list of Wordle words, but instead just a list of ints. Except that I don't exactly want to do that, because this partition words is also useful if I want to actually see the partitions. It might be interesting to do some other analysis other than max expected value. So what I really want to do is I want to have this function be overloaded. And then when I call the function, it can either produce a list of int or a list of Wordle words. So we can use class-based overloading to achieve this goal. So here, we're going to just say that it produces a list of answers. And now answer is going to be some type that could either be list of Wordle word, so that is an actual partition, or just the length of that list. And so how is that going to play out here? So here, now instead of Go taking a map from responses to lists of Wordle words, each response is now just going to map to what I'm calling an answer here. And this is also an answer. And now I get an error here. What's this error? Can't match type answer one with list of Wordle word. Expected type blah, actual type blah. Why is this? Oh, that's because I'm calling m.alter. Let's see. Down here, alter fun. This should now be maybe answer to maybe other answer. And let's see, now we're going to have a problem here. Couldn't match this, and that's because the old entry couldn't match it with Wordle word. Aha! That's because I'm taking possible answer and consing it onto this. So for this to be the right-hand argument of cons, then old entry would really have to be a list of Wordle words. Possible answer is one of the elements of this vector of Wordle words. This really is a Wordle word. The problem is I don't always want to cons it on. I just want to sort of include it in an answer. So that means that instead of just cons here, I really want to, I'll just sort of say include. And what's include? Well, include is going to end up to be a class method here. So I'm going to have a class named answer where include takes a Wordle word and an existing answer and then produces a new answer. We have two instances of this. So one, we're going to have instance answer list of Wordle word where include is just the cons operator. And why am I getting an error here? Illegal. Oh, well, I need flexible instances. That's easy enough. Okay. So it likes this, but now there's still a problem down here. What's this problem? Oh, ambiguous type variable. Why is this an ambiguous type variable? I don't think this should be an ambiguous type variable. Arising from the use of include prevents the constraint answer list of A0. List of A0. Why does it want this to be a list? Maybe it's because of this f.concat. Concat, this just works over lists. I don't really want this to work over lists. So what I need this to do is, this is taking a maybe, and I want to convert it from a maybe. So I'll just say from maybe here, and this I really want it to take a maybe answer and then give me an answer. That's what this needs to do. So here, from maybe nothing is going to be empty, and from maybe of just words is going to be words. Okay, let's see. So now I don't want f.concat anymore, but I'm going to use this from maybe. And it doesn't like that very much. Oh, it could refer to data.maybe from maybe. Then maybe I'll just call this maybe to answer so that there's no confusion. Maybe to answer. Okay, and then this, maybe to answer. Oh, it still is unhappy? No instance for answer, answer to. Aha. So we haven't put the class constraint on. And all of these answer variables are actually independent of each other because I don't have, the answer is not in scope because I haven't said for all answer. So I'm going to say that here. And I think the way that some people like to do it is like this. And, oh, it's complaining about for all, legal, blah, blah, blah. I definitely want scoped type variables here. You thought you were getting optimization, but actually we get typed programming because that's what I do. But in this case, I really do believe we'll get an improvement. Okay, so we've done all of that. Let's see, now what do we have? No instance for answer, answer. That's because it can't work for any answer, but only something that is in our snazzy new little type class here. And let's see, do we have any remaining errors? So now we don't know this partition words because it's get lengths, and get lengths works over list of anything. It's not quite sure how we want to instantiate partition words. We're going to fix that in a moment because I want answer not only to be a list of Wordle words, but we're going to have instance answer int where we can just accumulate the length. So include is going to ignore the word. I really don't care what the word is, and I'm just going to add one. Maybe to answer, if I don't have an entry yet, well, that's just 0. And if we have an entry, then we're going to return that value. Okay, good. Now, instead of calling get lengths, well, I just call partition words directly. And type inference will determine that, in fact, I want to run partition words where this answer is really just int. Okay, let's see how that goes now. So I'm going to build, and let's see where we get here. Okay, we've compiled and we've built. Let's now run, again, measuring the number of allocations. Okay, we have a result. Let's see. So now, after overloading partition words to work on ints, instead of list of Wordle word. So we write a little bit of that down. And then this produces allocations like, oh, wow. When you put them right next to each other, just that one change, now it takes half as many allocations from that optimization there. Let's also, just out of curiosity, check time. And indeed, we also have the amount of time. Look at that. That was one easy optimization, and now we're already twice as fast just from doing that. Okay, the last thing here is I haven't written down the commit, so let me commit with where I am here. So we'll just add optimize partition words. Oh, and by the way, is it still producing the right answer? It is. It's just worth checking to make sure. And we should also check to make sure that Cabal test still works. Although I don't know that we're actually testing these particular functions that are being measured here. I forget. We could check those tests, but we're still passing the test suite, so that's good. And I did the commit, but then I didn't actually snaffle out the commit hash. So here is commit, and then I put the hash there. I think that's going to be it for now. Next time, we'll continue this with optimizations. Some of the other one that I'm thinking about trying is to think about this word representation. Right now, it's a map from characters to sets of locations, where each location ranges from 0 through 4. But a set of locations that range from 0 through 4, that can be just represented in 5 bits. And so a map from characters, there's 26 characters to a set of to a set of locations where each one is 5 bits. So we can probably fit that in 130 bits, which is probably a lot less than it's taking now. So further adventures await us, as well as a tour, not a tour, but an application of Criterion for performance measurement. Hope this was fun. So long.